So we've talked about a few initial results of interesting things that happen with triangles. In Euclidean geometry, we found these triangle centers that have some interesting properties. 3 of them are collinear. We talked about the Simpson line. We proved some things about how the angle bisector divides opposite sides. And today, we're going to talk about a couple other theorems that have to do with triangles. And one of which especially is useful for proving that centers of triangles exist. There are many more centers than the ones we've found. And these are going to be useful down the road. Part of your assignment is going to be constructing some GeoGebra sketches that illustrate these, but for purposes of talking through proofs and understanding them, I'm going to just be drawing them here rather than showing you in GeoGebra. So, I encourage you as we go through this to, if you have the availability of another screen or if you can open up another window on your computer, to follow along in GeoGebra and make a construction to match this and kind of check and work on it as you go along. Okay, so we're going to start with Menelaus' theorem. I guess I don't need the extra S. Okay. Menelaus' theorem. I'm going to draw a picture to help me illustrate it first, and then I'll write it out as we go along, and then we'll talk about proving it. So let's say that I have this triangle, A, B, C. Now, I can extend the 3 sides if I want. So if you're in GeoGebra, you can just construct a triangle and then construct a lines through every pair of vertices to kind of see how this goes. Okay, and then I can construct a line that intersects these 3 sides, possibly the extension of the 3 sides. So, or of one of the sides. It could be the extension of all 3. So basically any line that is not parallel to one of the 3 sides. Okay, so if it's parallel to one of the 3 sides, it's not going to intersect that side. As long as it's not parallel to any side, it's going to intersect them at some point. Okay, so I have 3 points like so. Okay, I'm going to call them G, H, and I. Okay. Now, the claim of Menelaus' theorem is that if 3 points, one on each side of a triangle, extended if necessary, are collinear. Okay, so if the sides could be extended if necessary. So if these 3 points, one on each side, are collinear, then the product of the ratios of division of the sides by these points is -1. Now it's -1 if internal ratios are positive and external ratios are negative. Okay. Now, what I mean by that is if with the example I drew here, 2 of these are internal ratios. So here we would say that AG, GC, that ratio is a positive. AH, HB, that is positive. On the other hand, here we have to look at CI, IB. That ratio is going to be negative because it's an external ratio. Okay, so that's what our claim is. Our claim here is that if I take AG over GC times CI over BI, that would be the negative one, times AH, let's say BH over HA, that's going to equal -1. So notice I went around it here. AG to GC, and then I did CI, BI, or IB, BH, HA. Okay, so you work your way around the triangle to do this. All right, so how do we prove this? So first, we say G, H, I are collinear points, and we can just say as shown in diagram. Okay, and then our strategy here is going to be to draw in a few extra points. I'm going to draw them in green. So I'm going to go from C, I'm going to extend a perpendicular to this line, and I'm going to do the same thing from A, and I'm going to do the same thing from B. So I'm going to create all these perpendiculars right here, and I'm going to call these points, for consistency, D, E, and F. So D is the one that comes from A, B from E from B, and F from C. Okay. All right. Now the thing to notice here is that once I have this, I have all these right triangles. Okay. So I have these two right triangles, for instance. Now notice we have vertical angles plus their right triangles, so that's angle, angle. So these triangles must be similar. So we note that triangle ADG, this little guy right here, okay, is similar to triangle CFG, which is this larger triangle that I started to color in. Okay. Similarly, triangle BEI, right? BEI must be similar to triangle. Well, we want to look at the one relative to C, so we're going to look at this big triangle right here. They share an angle and they're both right. So triangle CFI, and finally, if we look at triangle BEH, so this triangle right here, I need a different color. This triangle right here, it's similar to this triangle right here. Okay, so triangle BEH is similar to triangle ADH. Okay, now all that's good because similar triangles have constant side ratios. So if we look at the first one, we can consider ratios here. So for instance, I can look at the hypotenuse of this first set right here, where, and I need a different color to kind of emphasize this, we take AG and GC. AG must be to GC as AD is to the corresponding leg CF. Okay? That's from the first set. From the second set, which you remember is with C and B, this smaller triangle, here we can take CI, the hypotenuse of the larger triangle, is to IB, the hypotenuse of the smaller triangle, as CF is to BE, right, corresponding right here. except by the convention we've identified, external ratios are negative. So CI is to IB must be the opposite of that, okay? CF is to BE. So we actually have, that's where our negative comes in. And then finally, in our last triangle, BH is the hypotenuse of this blue triangle, is to AH or HA, as BE is to AD. Okay, right here. Corresponding parts of the triangle. Okay, now, here's why all that's useful. Now we can look at what we want to look at. We want AG over GC times CI over BI, CI over BI, times BH over HA. Well, according to these, AG over GC is equal to AD over CF. CI over IB is equal to the opposite of CF over BE. And BH over HA is equal to BE over AD. So it's really just a question of picking out the ones we want to see. And CF, BE, BE, AD, and we have the negative, so this just becomes -1. And we're done. Okay? So that's Menelaus' theorem. That if you have these three collinear points, then we get these three collinear points, then where we have one on each side of the triangle. If you define the ratios in a certain way, the product of those ratios is -1. Okay, and it turns out the converse is also true. Okay, the converse is that if the product of the ratios of division of the sides by 3 points, one on each side of a triangle, extended if necessary, is -1, and this is again internal positive, external negative, then the 3 points are collinear. Okay. Now, this turns out to also be true. The proof is in your book. Basically, you assume that, you take a triangle. You assume that, if we extend this out so far, that this, like so, you assume that they're not collinear. So assume, like, if you have E and F, assume it meets at a different point out here. That's not the extension on, like so. So you assume they meet at a different point, and you just show that those 2 points have to be the same. Okay, I'll let you read the details of that in book. That is on page 167. Okay, so I'm going to let you read that one on your own. But this goes both directions. So this turns out to be an if and only if statement. Okay. Now, so the next one we want to talk about is Ceva's theorem. It's a C. And again, we will do this by thinking about a picture. Okay, so let's say we have this triangle A, B, C. Now this time we're looking at, say we have three lines, that join 3 points on the outside, or on the 3 sides. Okay, we want to show when they will be concurrent. Okay, so let's say we have these 3 points. D is opposite A, E is opposite B, F is opposite C, and they're going to be concurrent at this point G. Okay. So Ceva's theorem says 3 lines that join 3 points, one on each side of a triangle, to the opposite vertices. So just like we're talking about D and F here, they join the opposite vertices A, B, and C. These are those 3 lines are concurrent. That means they meet at a single point if and only if the product of the ratios of division of the sides is 1. Okay? In other words, G exists if and only if we take AF or sorry, not AF, AE over EC times CD over DB times BF over FA equals 1. This is what we're saying. Okay? And this is an if and only if statement. Now you can see how this will be helpful for proving the existence of these centers that we've kind of justified in GeoGebra, proven a little bit, but how do we know that they exist? Well, Ceva's theorem actually gives us a really nice way to do this. Okay? So here's the strategy. The strategy here is if we have this thing, let's look at this triangle, ABD. Okay, so we have these points as shown. So in the proof, we're going to say the points, suppose points as shown. Okay, so this, by the way, is just the one direction. We're going to say suppose they're concurrent. Okay, so if they're concurrent, we're looking this direction now. Then the product of the ratios of divisions is 1. Okay, so the supposed points are as shown. So what we're going to do is we're going to apply Menelaus' theorem to triangle ABD and line CF. Okay, so notice that we have CF, right? We are hitting the extension of side BD. We are hitting side AD. We are hitting side AB. Okay? So by Menelaus' theorem, we know that if we take AG over GD, right? So we take AG over GD, and then we take DC over CB and BF over FA, that has to equal -1. Okay? Now, next, we're going to apply Menelaus's to triangle ACD. Okay? and line BE. Okay. Again, it intersects the three sides at these 3 points. Okay, so in that case, then we have AE over EC times CB over BD times DG over GA. That has to equal -1. Okay? So then we just take the product of these two things. So we take AG over GD times DC over CB times BF over FA times AE over EC times CB over BD times DG over GA, and that equals -1 times -1, which of course is 1. And lovely things happen here. DG, GD. Right? CB, CB. GA, AG. Okay? And so what are we left with? We're left with AE over EC, DC or CD over DB, and BF over FA. So we get AE over EC times CD over DB times BF over FA equals 1. And that's what we wanted to show. So it turns out that those do, one direction here we've shown so far is that if they're concurrent, then the product is equal to 1. Now, how do you prove the other direction? Well, to prove the other direction, you just kind of go from here, right? So we start with this right here. If we start with this, we just expand it, okay? And if we can expand it as so, like so, then we could say we can get these products right here, and then we use Menelaus' theorem, of course, works in reverse, right? Like the converse is also true. So therefore, the points are collinear. So really, you can kind of work backwards on this in order to get the other direction. Now, this is really nice because it's if this is true, if Ceva's theorem is true, there are a few things we can prove. So take, for example, the medians, right? The medians split the three sides up, right? So A, B, C, D, E, F. So the centroid exists because if we do AE over AEC times CD over DB times BF over FA, well, that just equals 1 times 1 times 1 because these are midpoints, and that does equal 1. And so centroid exists by Ceva's theorem, okay? Similarly, if we take the angle bisectors, you can use the theorem we talked about last time and say, oh, they divided up proportionally, so use that, therefore, to prove that the angle bisectors must meet at the end center, okay? And there's actually another interesting point that we can discuss, prove in a similar way. So, again, I'm going to have you look at this on GeoGebra on your own, but if we look at the end center, okay, remember, the end center came from, we looked at the angle bisectors, right? And the nice thing about the angle the end center is that it gave you the inscribed circle of the triangle. Right? The inscribed circle. So let's say this is A, B, C, for instance. Okay. So it turns out the points of tangency, where this end circle actually hits the sides, okay, if we join the, and notice those are not the same as the points where the angle bisectors hit. If we join those to the opposite vertices, we will get a point right here, and it's called the Gorgonne point. Okay. And this is the segments from vertices of a triangle to points of tangency of the end circle with opposite sides are concurrent. And like I said, we call it the Gorgonne point. Okay. Now, the key realization here is that, hey, look, these are points of tangency. This is an exterior, so to point of tangency, these actually have to be congruent. Turns out these have to be congruent, and these have to be congruent. Okay. So to prove this, we really just need to say, we note that A, well, let's give this some names, D, E, F. So AE equals AF, and CE equals CD, and BD equals BF. Okay? So then we just have to look at the ratios like for Ceva's theorem. So then if we take AE over EC times CD over DB times BF over FA. Well, according to that, AE equals AF, or FA, so those cancel. CE equals CD. CE is the same as EC. And BD equals BF. So we get all these cancellations, and this just equals 1. So by Ceva's theorem, the lines are concurrent. Okay. Like I said, what you're going to do from here is you're going to do some problems related to this, and you're also going to go on GeoGebra and illustrate these theorems using that dynamic geometry environment. And to kind of justify, if you drag this around, if you drag the triangle around, that Gorgonne point still exists, no matter what. And Ceva's theorem holds, and Menelaus' theorem holds in lots of different examples. Okay, so these are some really useful theorems, some really, again, fascinating geometry of the triangle. So we're going to play around with that, and we're going to do some more cool stuff with it tomorrow.